I'd like to walk you through the process of charging and discharging a capacitor using the Simulink program, as displayed on the screen. This program solves the differential equation that governs the capacitor's behavior. First, let's look at the summing block, which represents our differential equation. On the right side, the summing block calculates the derivative of the capacitor voltage, multiplied by R times C. This matches the left side of our differential equation. Essentially, the equation states that this is equal to the right side, which is the source voltage minus the capacitor voltage. Therefore, both voltages must be present on the left side of the summing block. The signal line carries the source voltage, generated by the pulse generator. I'll show you the shape of the source voltage shortly. At the bottom of the summing block, we find the capacitor voltage, which comes back from the right side of the program in the feedback loop. Is the capacitor voltage really on this line? Yes, it is, because this signal line contains the derivative of the voltage multiplied by the time constant, which is R times C. In this part of the program, the time constant is calculated and displayed. The division block then divides out the time constant, leaving us with the time derivative of the capacitor voltage. To find the actual capacitor voltage, we feed the derivative into the integrator block. The output of this block gives us the desired capacitor voltage. Don't forget the initial condition: set the capacitor voltage to 0 volts at the start. This is noted above. The time constant is calculated from the resistance and capacitance of the capacitor and remains constant throughout the simulation at 1 millisecond. It indicates how quickly the capacitor can charge and discharge. The smaller the time constant, the faster the process. On the left, we have the source voltage, which is a pulse-shaped signal. We'll soon change its frequency. As the pulse frequency increases, there comes a point when the capacitor can no longer keep up with the rapid changes, meaning it can't fully charge and discharge. All this demonstrates the dynamic behavior of the capacitor in real-world applications. The goal now is to crank up the frequency of the square wave voltage and see how the capacitor reacts. As we increase the frequency, the period shrinks, and we can calculate it with this formula. For instance, at 20 Hz, the period of the pulse signal is 50 milliseconds. The big question is, what happens to the capacitor's charging and discharging as this period keeps getting shorter? In the pulse generator block, we'll set the amplitude to 1 volt and kick things off with a frequency of 20 Hz, giving us a period of 50 milliseconds. The stop time at the top of the program is set to 0.1 seconds. We next run the program. Here's what the generated signal looks like. The source voltage is spot on with an amplitude of 1 volt and a period of 50 milliseconds, repeating itself perfectly. You can see the period indicated below. Now, what does the capacitor voltage look like? To find out, I'll click on this scope to reveal both voltages. The blue line represents the source voltage, while the red line shows the capacitor voltage. In the initial part, the source voltage remains constant, charging the capacitor quickly. The capacitor hits the 1 volt mark in no time, effortlessly keeping pace with the source voltage. Then, the source voltage flips from 1 volt to -1 volt, and the capacitor discharges just as swiftly, hitting -1 volt shortly after. Again, the capacitor keeps up without breaking a sweat. From this point, the cycle repeats. In conclusion, the capacitor easily handles fully charging and discharging because the frequency of the square wave voltage isn't too high. With a period of 50 milliseconds, much longer than our 1 millisecond time constant, the capacitor has no trouble following the source. At this low frequency, the amplitude of the capacitor voltage matches the source, ranging from 1 volt to -1 volt. We're cranking up the frequency to 100 Hz, which means a period of 10 milliseconds. This is still quite a bit longer than our 1 millisecond time constant. Let's see what happens. In the pulse generator settings, we reduce the period by a factor of 5. We also cut the stop time at the top of the screen by 5, setting it to 0.02 seconds. Now, let's run the program and check out the scope. As expected, the period is indeed 10 milliseconds. From the graph, we can see that the capacitor can still fully charge, just reaching 1 volt. The same goes for discharging, it manages to hit -1 volt. So, at this frequency, the capacitor is just about able to keep up with the source voltage. But can we verify that the time constant is really 1 millisecond from this graph? Remember, when charging, after one time constant, the capacitor voltage should reach 63% of its final value. In this case, with a final value of 1 volt, the voltage at one time constant should be 0.63 volts. To check this, we use the cursor measurements button. Crosshairs appear on the graph. We set the right crosshair to the capacitor voltage, then enter a time of 1 millisecond. Sure enough, the capacitor voltage is nearly 0.63 volts, just as predicted. Don't forget to click the icon again to remove the crosshairs when you're done. We're going to increase the frequency even further, to 200 Hz, making the period 5 milliseconds. This is still larger than the time constant, but it is getting closer to it. We need to adjust the settings in the pulse generator block accordingly. We also set the stop time to 0.01 seconds to avoid showing too many cycles. After running the simulation, we get the following result. For the first time, we see that the capacitor does not fully charge and does not reach 1 volt. Likewise, it doesn't reach -1 volt because it doesn't fully discharge. The pulse-shaped input signal is a bit too fast for the capacitor. Additionally, we notice that the peak-to-peak value of the capacitor voltage is smaller than that of the source voltage. We will see shortly that this trend of decreasing peak-to-peak value continues at higher frequencies. Finally, I set the frequency to 1000 Hz, which means the period is now equal to the capacitor's time constant, 1 millisecond. First, we again have to adjust the settings in the pulse generator block. I left the stop time unchanged. Here's what the results look like. There are more fluctuations, so let's focus on the right side of the graph first. You'll notice that the amplitude of the capacitor voltage stabilizes, but it's clear that the capacitor voltage, in red, is much smaller than the source voltage, in blue. Why? The capacitor simply can't keep up. It doesn't charge and discharge fast enough, just like we saw at lower frequencies. As the capacitor starts to charge, the source voltage flips polarity too quickly, so discharging begins before the capacitor can fully charge. If the source voltage of 1 volt were held longer, the capacitor voltage would eventually reach 1 volt, as I'm demonstrating now. But the capacitor doesn't get that time, since it's already started discharging. The same goes for discharging, it's only partial. If the source voltage of -1 volt were maintained longer, the capacitor voltage would follow suit. But again, the capacitor doesn't have enough time to fully discharge before the voltage jumps back to 1 volt. The bottom line is that the capacitor can't react quickly enough, so the amplitude of the capacitor voltage ends up being much smaller than that of the source voltage. It's no surprise that if we push the frequency even higher, the amplitude would shrink even more. This really underscores the importance of the time constant. You need to compare it with the period of the alternating signal to understand how the capacitor will behave. Over time, the amplitude of the capacitor voltage will stabilize, but in the beginning, it's a bit chaotic as the capacitor adjusts. This initial phase is known as the transient response. To sum it up, at low frequencies, the capacitor has plenty of time to fully charge and discharge. This means it can keep up with the pulse signal, and the amplitude, or peak-to-peak value, of the capacitor voltage matches that of the source voltage. But as the frequency increases, the capacitor starts to struggle, it can't fully charge and discharge in time. As a result, the amplitude of the capacitor voltage drops below that of the source voltage. The time constant is the key here, it's what separates low from high frequencies. When the period of the signal is much longer than the time constant, the capacitor can comfortably charge and discharge completely. But when the time constant is shorter than the pulse signal's period, the capacitor only manages partial charges and discharges. However, no matter the frequency, the capacitor voltage frequency always matches that of the source voltage.